Okay, so welcome back everyone to the Isogeny Club. It's my pleasure to introduce Ilinca Radulescu, who will be talking about forensic categories. The floor is yours.
Cool. So thank you for inviting me to give the talk. So this is a joint project we submitted with Andrea, Luca, Sika, and Benjamin. And hopefully it will be available on ePrint soon. So yeah, let's get into it. So this is the overview of the talk. So I'm going to start with some motivation for coming up with a framework in the first place, and then some background on categories, and then introducing these notions that we came up with, which is effective categories and the fingerprint. And then I'm gonna show an instantiation of a forensic category, and then talk about two protocols, and then a conclusion. Cool. So I'm gonna start with the motivation then. So we wanted to do this project to kind of extract the essential features of SQIsign. So we all know there's a lot of versions, but they all share similar structures. So it's a bit confusing. So the idea was to kind of just take the essential parts and hopefully make the SQIsign protocols more clear in that way. And also it's quite heavy on the algebraic machinery. So you need a background on elliptic curves and algebraic geometry and so on. So we aim with this framework to kind of get rid of all of that and then make it more accessible conceptually. And then hopefully more people can understand it as well, which can lead to better implementations if more people work on it. So that was another motivation. And then another motivation, which is not related to SQIsign at all, is to have a new perspective to formalize concepts like SQIsign or other cryptographic primitives, just using category theory, basically. So then going into the background, what are categories? So we only need to know these basic definitions of categories for the framework. We don't go into any details or more complicated axioms. And it's just that you have a category which is defined by a set of objects and a set of morphisms, and they have to have the following properties. So you have a morphism has a domain object and a codomain object, and we denote it like so. And then the set of all morphisms with domain D and codomain C is called the home set. And this is just the same as in elliptic curves and isogenies, the same notation. And then we also have this composition law. So if you have a morphism from A to B and another morphism from B to C, then you have a morphism going from A to C. So you can compose morphisms, and this is associative. And then lastly, for every object in your category, you have an identity morphism that maps the object to itself, basically. And this is really all we need to know about categories to construct a framework. So it's meant to be quite easy to grasp. And then to build the framework, we start with introducing effective categories. But before that, we have to introduce pre-effective categories. And in short, all pre-effective categories do is just turn the axioms that we had for categories into computational axioms, because we can't use the axioms from before to build anything in relation to cryptography. So this is like the official definition that we give in the paper. And is a category with algorithms such that the following holds, and you need every object to have a unique representation as a binary string, and you need polynomial time algorithms that can solve the following. So yeah, given n and a binary string, decide whether encodes an object or a morphism in your category. Then the next one is given an endomorphism to compute the domain and the codomain object. And then to be able to compose morphisms. So if you given two morphisms, then you have to return the composition. And then lastly, given n and an object in your category, compute the identity morphism. So this is what a pre-effective category does. And then once we have this, we can start working towards our effective category. So the next thing is we need a walk. So to be able to move between objects, this is where the walk comes in. And we need to introduce a negligible function to define a walk. This is just the standard definition, and it's just a function from the natural numbers to the real numbers. And it's negligible if there exists an integer x0 such that for any x larger than x0, and for every c in the natural number, this holds. And then we define a walk in a pre-effective category as a pair, where a walk is an algorithm, a deterministic polynomial time algorithm, which takes as input an object A and a sequence of random coins and produces this pair B and C, where C is the morphism from A to B, basically. And mu is the distribution on objects, such that when R is a sequence of n uniformly random coins, the statistical distance between mu and the distribution of the output's codomain is a negligible function of n. So what does this mean? It means that the distribution of B's, the B's here, is almost indistinguishable from the distribution mu. So this is very similar to what we have in isogeny walks, basically. And that was the idea, just to emulate that. And now we can finally build our effective category, which is just a pre-effective category with a walk and also an origin object that we know the representation of. So yeah, this is the official definition. It's just a pre-effective category and an origin object that you know the representation and can be computed in polynomial time. Cool. So now we have an effective category, but this is still not enough to construct anything from it. So no cryptographic protocols, and especially no SQIsign. We needed to add further structure to our category. So this is where the fingerprint comes in, and hence the name forensic categories. So what is a fingerprint? So a fingerprint on a category. So you have your category and then you add the fingerprint on the category. Is a collection of maps from the home set to some set mu. And then we also allow for undefined values. And M has to be finite and contain at least 2 fingerprints. So yeah, for the same category, you can have multiple fingerprints. So in the paper, we actually, for the same category, we present 2 possible instantiations of the fingerprint. So yeah, you can change your fingerprint for the same category, and the fingerprint is specific to your category. Cool. And then to finally obtain forensic categories, what we need is an effective category with a fingerprint, but the fingerprint has to have special properties. So what are the special properties? Effective, hard on average, triangularizable, and computationally walk indistinguishable. And now I'm going to go through each property in more detail to explain what's happening. And just to make it clear, if you have an effective category and the fingerprint doesn't satisfy one of these properties, then you don't have an forensic category. The idea was to, when we were constructing the framework, was to come up with a list of with a set of minimal assumptions on the fingerprint that were basically necessary to construct a framework. Yeah. And then, so effective, this is quite intuitive. It just means that given the morphism, computing the fingerprint of the morphism is efficient, so it can be done in polynomial time. The next one is hard on average. So this looks a bit more complicated, but what we're saying is that you have this language L and finding a witness. So this pair A together with the two morphism phi and C should be hard. And phi and C must satisfy the following. So they both go from A to B. They have distinct fingerprints and the fingerprints are defined. And we say on average because A has to follow distribution mu. And what this is saying is that it should be hard to find something that looks like this. So your morphism going from A to B, both of them, so between the same two objects, and they have to have distinct fingerprints. So this kind of looks like the 1N problem, and this is where we came from. Since 1N is hard, the idea was to find something similar here, but without introducing a dual, without defining what a dual morphism would be. And we introduced the fingerprint to kind of deal with that aspect. So yeah, basically it should be hard to find this pair of morphism between the same two objects. Cool. And then the next one is called triangularizable. And you have this PPT algorithm, which is called triangle. And then you input two morphism, phi and psi, going from O to A and O to B. And the fingerprint and the algorithm returns this third morphism from A to B of the given fingerprint. And the distribution only depends on A, B, and M. And what's important is that your input morphisms really have to go from the origin object O. So you can only input morphisms that start from O for triangle to work. So it looks like this, hence the name triangle, because the diagram looks like a triangle. And the algorithm would output this morphism chi here from A to B, and the fingerprint of chi is M. Cool. And then computationally Wook indistinguishable. It says that you have an algorithm, a PPT algorithm called SymWook, which takes an object A as input and returns a morphism going from A to B. And this is indistinguishable from the output of triangle. So this chi is indistinguishable from this chi here. And this is the algorithm that we give in the paper, which shows the oracles of the Wook distinguish experiment. So you either run SymWook and it returns chi going from A to B, or you run triangle where you Wook from O, you sample a fingerprint, and then you input these morphisms like here. Like here. And then this chi is indistinguishable from this chi, basically. And this is, I'm going to explain why we need this later, but just to give you an idea, this is how we get zero knowledge in our protocols. So we kind of assume zero knowledge. Great. So this is the framework. And this is all the properties of the fingerprint, the minimal set of properties that we need for a fingerprint. And now I'm gonna show an instantiation of a category and of the fingerprint. So hopefully it makes a bit more sense. So this instantiation of a forensic category is the instantiation which gives classical SQIsign, so one-dimensional SQIsign. So yeah, I'm only gonna go through one fingerprint in the instantiation. We do provide two. The other one deals with level structures. So yeah, it's in the paper, but I'm not gonna talk about it in the presentation. And how did we choose an effective category? So again, an effective category is a pre-effective category with a hook and an origin object. And our claim is that the category of supersingular elliptic curves in characteristic P is a category where objects are isomorphism classes of supersingular elliptic curves, and morphisms are just the isogenies between the elliptic curves. And isomorphism classes, we just mean the J invariant to have a unique representation of the objects. Cool. And now we claim that this category is effective. So we first showed that it's pre-effective. So we showed that all the computational axioms of a category hold. So yeah, like I said, because we use the J invariant, the objects have unique representation. And then we can decide whether an encoding is an isogeny or an elliptic curve. Cool. And we can compute the domain and codomain of an isogeny. This is quite trivial since when we code the isogeny, the domain and codomain are part of the coding of the isogeny. So it just follows from there. And then we know we can compose isogenies. So this also follows quite naturally. And then we know for every elliptic curve, you have an isogeny which maps the elliptic curves to itself. So great. We have our pre-effective category. And now we just need to show that we have a walk. And then, like I said, walk was just emulating the walk that we already have in isogeny graphs. So we instantiate this by following a non-backtracking random walk of length n from the input curve in the L isogeny graph. I guess everyone's quite familiar with isogeny walks and how you have an L isogeny and an L isogeny and so on. And we also have the desired distribution and the statistical distance because our graph is Ramanujan. So the distance between the distribution of the output of the walk and the stationary distribution is a negligible function. So, you know, the elliptic curves are uniformly distributed, but the distance in this case between the stationary and the uniform distribution is negligible, so great. So we also have the walk, and then to obtain an origin object, this is a result that already existed. We're just making use of it. We just have an algorithm to find a supersingular curve A0 of known endomorphism ring for any parameters. Cool. So I guess that was quite intuitive that we're going to go with elliptic curves and isogenies for our category. And now it remains to show that we can also have some sort of fingerprint with the desired properties. So this is the fingerprint. Like I said, it gives classical SQIsign, and we call it the kernel fingerprint. So this is the pre-fingerprint, and it's not the fingerprint because it's not an efficient encoding. So yeah, so it's easier to work with in terms of showing all the mathematical proofs, but it's not efficient in terms of computations. So let phi be an isogeny between E and E prime. And these are so an isogeny between two elliptic curves, and define the kernel of phi n as the kernel of phi with the intersection of the n torsion points of E. So your starting curve. And then if this intersection is isomorphic to a cyclic group of size n, so z and z, then your fingerprint is defined, and that is your fingerprint, this intersection. If it's not isomorphic, then it's not defined. And like I said, this kernel, working directly with the kernel is not efficient. So what we noticed is what we noticed is that obviously you have a cyclic group. So it can be generated by a single point P. Sorry, that's meant to say N, not Ln, sorry. So you have a single point P that generates the whole cyclic group, and this P can be written, this P is in the intersection of the kernel and the N torsion points. So you can write it as a combination of the bases of the N torsion points, so P1, Q1 here, are the bases of En, and you can write any point in there as a combination of their sum. So we just use A and B to actually encode the fingerprint. And A and B are known, oh sorry, not A and B. The bases P and Q are known. So this is why this works, sorry. And then since we want some sort of unique representation of the fingerprint, then we take the normalized version. So we multiply by the inverse of A. If A is invertible, of the inverse of B. If A is not invertible, one of them has to be invertible. Otherwise, the size of the group is smaller than N. So this would not be true. And then we also allow for undefined values. So this is the kernel fingerprint. And now we're going to show that this kernel fingerprint satisfies all of those 4 properties. So we claim that it's effective. So given an efficient representation for an isogeny phi, we first compute the pre-fingerprint by evaluating it on the N torsion points. And then to compute the actual fingerprint of phi, we use a generalized discrete logarithm computation, and this takes time polynomial in log n. So if we choose n to be smooth, then this is efficient. And yeah, in the paper, we assume n is smooth to obtain this. Cool. So great, it's effective. Is it hard on average? So the strategy to this is to show that if the fingerprint doesn't satisfy the hard on average property, then one end is not hard on average either. And then isogeny is not hard in the worst case. This is a result by Benjamin and Arthur, where they show like all these problems are equivalent. So that's the strategy. How do we actually do this? So assume the fingerprint is not hard on average. Then you have this PPT algorithm, which takes as input a uniformly random curve V1. And then A returns the pair phi psi going from E1 to E2, such that this is in the language. And how do we solve one end from here? You let E1 be uniformly random, and then you run the algorithm and you get this pair back, like so. Cool. So this is what the algorithm gives you, because what we said is that for the 2 isogenies to be in the language, they have to go between the same 2 elliptic curves and have distinct defined fingerprints. So we simply, sorry, my slides are not working. Oh, it's working, cool. So we simply return this composition going from phi and then the dual of C. And this gives an endomorphism of E1. So we have a solution to the 1n problem. Of course, there's a little technicality here. Since we haven't actually used the fingerprint at all, we have to show that we have to show the endomorphism is not trivial, so it's not scalar multiple. And this is where the fingerprint comes into play. Because if assume this endomorphism is trivial, then you have A and B integers, and you can write your two isogenies has A phi and then B psi. But then if this was the case, then since A and B are just scalar, they wouldn't affect the kernel, and also coprime to n. They wouldn't affect this intersection between the kernel and the n torsion points. So then phi and psi would have the same fingerprint. So because, and this would contradict the fact that they're in the language where they have distinct fingerprints. So yeah, this is where the fingerprint comes into play. It's to show this holds, and you always get a non-trivial endomorphism, basically. Cool. So I hope this makes sense. So yeah, we also get Howden average for the kernel fingerprint. And now how do we get our triangle algorithm? Well, our input is these two isogenies, phi and psi, going from E0. So E0 if the special curve of known endomorphism ring, and then AB is a fingerprint. So this is what it looks like so far. And then we know finding an isogeny between two given elliptic curves is a hard problem. So how do we solve this? So first of all, let P0, Q0 be the chosen basis of the n torsion points of E0. And then let P be the point such that it's written as AP0 plus BQ0. So like I said, this is just the point which generates our intersection of the kernel and the E0 and torsion points. And then the first step is to use Velou's formulae to compute this quotient isogeny here. And we know this isogeny, so the phi Velou has the desired fingerprint because it's just the kernel between the intersection of the kernel and the n torsion points is exactly AB is what we want. But we still need to complete this circle here. So we need to make sure we do it in such a way that we leave the fingerprint unaffected. And to do so, we use signing KLPT in an L prime graph. And L prime and L are coprime. So what we do is just use KLPT to compute an isogeny going from this quotiented curve to E2. And since we walk in two distinct graphs, so L isogeny and then L prime, and the L and L prime are coprime, then the fingerprint remains unaffected. And then this is exactly what triangle does. It would do this whole step 1, 2, 3, 4, and then it would return the composition of phi Velou with psi KLPT, and this would be your response isogeny of with the desired fingerprint, since the KLPT is done in L prime. Cool. So we also get triangle with this algorithm. And then how do we get walk indistinguishable? Well, this is how we simulate CMOOC. Your input is E1. And then, oops. Cool. And then again, you have P0, Q0, the chosen bases. So this is the same as in triangle. And again, we use value here to compute our quotiented isogeny. And this isogeny has the desired fingerprint. But how do we get to E2? Well, what we do is we take a random walk in, again, the same L prime isogeny, where L prime is co-prime to L. And this N here is just so that we ensure E2 follows the uniform distribution. So N has to be large enough and N is fixed. And you have this isogeny sigma. And then what CMOOC would do, so it runs this, and then it would return this composition tau sigma between the two elliptic curves. Okay, so is this actually indistinguishable from the output of triangle? Well, the purple parts are generated in the same way using Value's formulae. So they're going to be indistinguishable. And the fingerprints, again, are chosen or random. So that's also fine. So we just need to make sure this sigma part of the composition is indistinguishable. And this works because we actually assume that the output of signing KLPT, which is the KLPT algorithm used in SQIsign, is computationally indistinguishable from uniformly random cyclic isogenies of same degree and same domain. So we fix this N to fix the degree of the isogeny, and they have the same domain and codomain. They go between the same two isogenies. So without this assumption, then we couldn't get WOOC indistinguishable. So this is, this assumption is how we get the fingerprint satisfying this valuing property, basically. Cool. So I hope this makes sense. So this is one instantiation. Like I said, we also have a level structure instantiation where we go through all the properties again. And now I'm gonna start with a digital signature. And the instantiation of the digital signature would be classical SQIsign with the previous instantiation. Cool. I'm gonna assume everyone is quite familiar with SQIsign, so I'm gonna go straight into the Sigma protocol that we present in the paper, which aims to mimic SQIsign. But if there are any questions, please let me know. So the first step of the Sigma protocol is to generate a secret key and a public key. And to do this, we're gonna walk from O, our origin object, and then the isogeny, the morphism phi is going to be the secret key and A is going to be the public key. Then the next step is the commitment step. So the prover walks from O to B to generate B, MC, and B is the commitment object, and is the commitment object. And then he sends B to the verifier. And what the verifier does is they sample a fingerprint and they send this to the prover. So, of course, the fingerprint in our instantiation is a kernel, whereas in classical SQIsign, the challenge would be an actual isogeny. But since an isogeny is uniquely determined by its kernel, then the two are equivalent. So this is why we can use this fingerprint for a challenge. And then what the prover does in the response phase, well, they simply run triangle because they have access to the secret key. So they run triangle with phi, psi, and m. and they just return this morphism C response, and the response isogeny has the desired fingerprint. Because that's what triangle does, and then, cool. And then in the verification process, you accept this morphism, Cyrus, if it has A for domain, B for codomain, and then the desired fingerprint. So this is what a Sigma protocol looks like. And now to actually show that we can obtain a digital signature from the Sigma protocol, we're going to show that it's special sound first. And we say, so the official name for this Sigma protocol is FC Sigma for forensic category Sigma, and MathCalci is the category in which you work in. And such a protocol is special sound if given to accepting transcripts, so B Cyrus and B and prime Psi prime resp, and they have the same commitment B and distinct challenges, so M and M prime are distinct. Then you can find for a witness chi prime for A in L. And this just follows naturally by construction, because if you have these two accepting transcripts like described, then Psi prime resp is a witness, because you have something that looks like this, sorry. And this is exactly what the picture for the hard-on average looked like. Cool. So our Sigma protocol is special sound. And then how do we get honest verifier zero knowledge? Which is the final property to be able to use fiat Shamir and transform our digital signature, our Sigma protocol into a digital signature. So we have a secret key, and then what the simulator does on input this public key A is he would run simulk from A, and he would obtain this commitment object B, which follows distribution mu and chi. And then he would compute the fingerprint of chi. So whatever morphism he gets here, whatever morphism they obtain here, then they would compute the fingerprint of the morphism. Since this is effective, and then they would return this transcript. And this is indistinguishable from a transcript obtained by an honest run of the protocol. Well, like I said, in both B follows distribution mu, so great. The two fingerprints are uniformly distributed. And then because the output of simulk, so chi, is indistinguishable from the output of triangle, which is how we generate our response isogeny in an honest run of the protocol, then this is actually indistinguishable. So this is how we get zero knowledge. We basically, like I said, assume zero knowledge. Without the Wook indistinguishable assumption, we wouldn't be able to get this property, which is what we also do in classical SQIsign. And yes, this construction doesn't capture the HD variants of SQIsign, because we don't have any oracles that can instantiate this Wook indistinguishable property. So we're not able to instantiate the higher dimensional variants, just the classical one. And then a second protocol that we get is what's called the chameleon hash function. And to our knowledge, this hasn't been achieved in the isogeny-based setting before. And we're able to obtain this just through using the framework, just the forensic category framework, without looking at the instantiation. So that's pretty cool. Just getting a new scheme, a new cryptographic primitive just from the framework itself. So I'm gonna introduce what a chameleon hash function is. I'm not an expert, so I'm gonna give more of a general overview of this scheme. So yeah. Well, they're also known as trapdoor commitments. And they're trapdoor collision resistant hash functions parameterized by a public key. And the idea is that well, you generate your parameters first, and then you generate your keys based on the input parameters or the public parameters, and you have your pair of secret key and public key. And then the next step is where you hash. So on input a public key PK and a message, then you output the hash and the check value, which is also known as randomness. And then you have this check step where on input the public key and the message and the check value and the hash function, then you output a bit indicating whether the hash is valid. And this is where, the trapdoor part comes in, is that you can change your randomness. So if you input a key pair, so secret key, public key, and a pair of messages, and a check value, then you output a new check value. Okay, so this is all quite abstract. But the idea is that you can use your secret key to make a trapdoor and obtain a new randomness, basically. So this is the general view of how a chameleon hash function works. And then it needs to also satisfy certain properties. So the first one is correctness. So the output of both the hash and the change part of the protocol are always accepted by the check part. And then the second one is collision resistance. So there are different strengths to collision resistance. In our chameleon hash functions, in our chameleon hash function that we present in the paper, we can only get weak collision resistance. So that's why I'm providing the definition for the weak version, which says that without knowledge of the secret key, it's hard to find these pairs of message C and then message prime, C prime of distinct messages that both pass the check for the same hash. And then we also have indistinguishability. Again, this also comes in strengths. In this case, we're able to get the strong version. And the idea is that you can't distinguish between check values that were produced by hashing or by changing. So either by hashing or by changing your step in the hash function. You can't say whether C was produced. Yeah, you can't say which step you used to produce the C. And this is how we instantiate a chameleon hash function in our framework. So the properties that we had, the minimal set of assumptions, they were not enough to obtain a chameleon hash function. So we needed to introduce a bit more structure. So this is where G is a group which camouflages the fingerprint, and hash is a collision resistant hash function which goes to G. So we needed this assumption first, and then we could construct our chameleon hash function. And then the idea is that your public key will be an object A in your category, and your trapdoor is going to be the morphism going from O to A. Then to hash a message, we hash it to hash message, which is just using the hash function here, and use it to camouflage the fingerprint of this morphism psi going from A to B. And then to adapt a hash, the idea is to use your knowledge of phi, which goes from O to A, to invoke triangle and produce a new hash message of the fingerprint. So because you can use triangle, you can input different ends, basically. You can input different fingerprints, so you'll obtain different hashes. So this is like the big overview of how the hash function works. And then this is the in detail algorithm from the paper. And you can see each function. So to generate the key, you just walk from O, which is the same as in the digital signature. And then you just return the object as your public key and the morphism as your secret key. Then to hash, so yeah, if you note in hashing, we use the indistinguishable walk to obtain our object and our morphism. And then MH is the hash of the message acting on the fingerprint. And if you notice here, RC, so our randomness is a morphism, because we can obtain different morphisms for the same fingerprint just by using triangle, basically. So that's the idea. And then check is you just make sure if you hash or if you change, then your process is valid. And to change a message, we just do triangle, like I said. Sorry, to use the change, not change the message, but to use the C change of the protocol, we just use triangle. Cool. So now, do we get correctness? Yeah, we construct our chameleon hash function, so it never fails, basically. Cool. And then do we get collision resistance? So if we unpack the definition a bit, we let A be the public key. And then an adversary that wins this weak collision resistant game computes the following such that they both pass. Okay, so this is quite abstract. But this is what it actually looks like. Is if an adversary can find a weak collision resistance, then they can compute psi C, psi prime C, going between the same two objects, so two morphisms going between the same two objects, such that the hash acting on the fingerprint goes to MH, and then the second hash of the second message acting on the second morphism, they go to the same value. So our first option would be, that the two hashes are the same, and hence the two fingerprints are the same. We assume the group is free, so it's nice, we can do, we can have inverses and stuff. So if the hashes of the messages are the same, because we have the same MH here, then the fingerprints would also be the same. But since the two messages are distinct, it would mean that the hash function would hash two distinct messages to the same value. But this is a contradiction because we assume the hash function is collision resistant. So we can't have this option. The second would be, okay, the hashes are distinct then. So the fingerprints must also be distinct. But then if the fingerprints are distinct, then you find a witness for the hard language. And the adversary can't do this because this is meant to be hard. So you either find, if you find the collision resistance in the chameleon hash, you either contradict the fact that the hash function is collision resistant, or you contradict the fact that finding a witness for the hard language is hard. So this can happen. We don't. So we have weak collision resistance. Great. And then finally, this is strong indistinguishability, and this is the algorithm, the game that you play to get strong indistinguishability. And the idea, again, we rely on Wook indistinguishable. And when we hash, we use simOok to produce our randomness. And then when we change, we use triangle to obtain our randomness. And Wook indistinguishable says that you can't distinguish, you can't say whether a morphism was obtained using triangle or simOok. So again, heavily relying on Wook indistinguishable to get this property. Yeah, cool. And that's it. This is how we get our chameleon hash function. Success. And then conclusion. So this is like feature work and what we can do next. So first of all would be to instantiate the framework in a different setting, such as lattices. So everything we present in the paper as well is based, of course, they all started with SQIsign, so it's all focused on isogenies and elliptic curves and so on. But could we work in a different category, possibly using lattices? I know this was suggested before when I given the talk. And then the next one would be, can we obtain any other schemes in the framework? What assumptions would we need to add? So like I said, even to get a chameleon hash function, we had to add this group acting on the fingerprint. And we also assume we have a collision resistant hash functions. We couldn't really show that. So yeah, can we get any other schemes in this framework? And then can you extend the framework, for example, to instantiate the higher dimensional? So we could change Wook indistinguishable to be stronger, weaker, then maybe we would be able to get some sort of oracles and so on. But we just focused on the classical version for now. And yeah, oh, sorry, oops. That's it. Thank you. Questions? I'll get the slide back up, sorry.
Thank you. Are there any questions?
Thank you for the talk, Ilinca. Maybe I can start with a question. How about like seaside-like settings? Does it apply there? Basically, the category would be again like just restricting to the curves to find over FP and also isogenies to find over FP.
We haven't actually looked at seaside from what I remember. But is that more, I guess, yeah, I'm not sure just because we haven't actually looked. Some of the schemes we looked at were, I think, Antonines, VRF, and then like Ski Prime. But I don't think we've discussed any other ones, so I'm not sure. Yeah.
I don't know either. I just.
But I mean, yeah, it's good like future work, I guess. But yeah, I'm just not sure. Yeah.
Could imagine. Yeah. Oh. Okay, thanks.
Are there any other questions? I had a question, a more like specific question about the fingerprint.
Yep.
So you define the fingerprint in terms of this intersection with the end torsion.
Mm-hmm.
So I guess you fix n at the beginning and then you define it in terms of some n.
Yeah, so we would fix n and also all those, the bases of the curves before. And I guess every time, and I guess you would change it, like if you wouldn't use the same if you were to run the protocol differently, but yeah, you do fix it. You would fix the bases and the n before you start anything. It would be part of your parameters, I guess. Yeah.
And are there any properties you need on this n, or can it just be?
So for the kernel one would be just that it's smooth. I'm not sure on the level structures. I feel like there are a few more. But again, just that it's smooth so we can get a discrete log when we compute the fingerprint, basically. Yeah, that was the main one.
Okay. We also have another one in the chat. I can just read it out.
Yeah, thank you.
So Bruno asks, have you looked at instantiating the ring signature error ball, which I think is a ring signature based on SQIsign, through this framework, because it also uses KLPT?
So I don't, maybe more towards the end we've looked, but I don't think we've looked like in detail. We kind of just focused on really getting SQIsign, which is the digital signature, and also the chameleon hash function, since it wasn't done before. And there were a bit of technicalities as well with the hash functions that we had to work. So we didn't have a lot of time before the deadline to focus on other things. And I don't think we've discussed it like in the past or not in detail. So yeah.
Okay, there's another question. Vishnu asks, are there also other frameworks possible other than the kernel and level structure?
Oh, so these are like some of the instantiations we've proposed to show that this forensic category framework actually works. But yeah, I guess you can, a next step would be to see if we can change the category to lattices and see what kind of fingerprint we could attach to that. So yeah, we've just presented 2 fingerprints in one category, but I guess there are more depending on what kind of schemes you want to obtain. So yeah.
Okay. Are there any other questions? If not, then thank Ilinca again for the talk. And next, so in 2 weeks, we'll have our final talk of the season. And it will be given by Alessandro Sferlazza on computing traces of endomorphisms via p-adic lifting. So we hope to see you all there in 2 weeks.